Right, thank you. The point about new mathematics, I guess, comes from Kevin Buzzard, who has been very critical of previous efforts, saying that's very big, but it's mathematically trivial. I mean, he can be kind of mean. And he says, if you want to interest mathematicians, you've got to do something exciting, new, deep, sophisticated. So this is the thing I thought I would tackle. It involves Ramsey's theorem. Now, you've probably all heard of Ramsey's theorem already. If not, it's worth learning about because it has many uses in computer science. But this diagram shows an illustration where if you have 6 people at a party, it's the usual way they talk about it. You either have 3 people who all know each other, or 3 people, each of which do not know each other. Or to be a little more technical, if you color the edges, 2 colors, red and blue, then either you will have a triangle of red or a triangle that's blue if you have at least 6 vertices in the graph to begin with. And the point for Ramsey's theorem is that however big are these monochromatic cliques that you're looking for, you can find a Ramsey number which is big enough that these cliques will always exist. In fact, this theorem has a lot of powerful generalizations and is really one of the coolest things in combinatorics. So these Ramsey numbers grow rapidly. And we know in particular we have a lower bound of root 2 to the k and an upper bound of 4 to the k, where k is the size of the clique, the monochromatic clique that you're trying to find. That's assuming you want to find the same size k for whether it's a red clique or a blue clique. And this based of the exponent of 4 has been around since something like the 40s. So when some people came along suddenly and said, no, we can reduce 4 by 4 minus epsilon, and this epsilon is really quite small, it's like 1 or 1,000 or something, you might think, like, who cares, right? And that's certainly what many people would say about such a thing, but the mathematicians were spitting out their coffee when this was announced. So this is an exciting new result. Now, to try and lead up to how this proof works, not that I really understand how the proof works, here is a simple explanation. It's not really a proof, but it's an explanation of where this 4 to the k upper bound comes from. So imagine you've got your graph. Remember, it's a complete graph. All the edges are there. So every 2 vertices are connected by an edge. It's either red or blue. And you imagine throwing all the vertices of that graph into this set X. Now, at every stage, you are going to throw away up to half of the contents of X, but in a careful way. So you grab an element of X arbitrarily, and then you ask, how many red neighbors does it have? Remember, it's the edges that are colored. So how many other elements of X are connected to my particular one by a red edge? And if most of the edges are red, you take that little x and you pop it into A. You keep the other red neighbors and you get rid of the blue ones. And you keep doing this. Now you see what I have done. I've moved the little x to A, and all of its edges back to things in X will be red. That's what the coloring indicates. Now, if you keep doing this, you will have things in A, and it will be a red clique because everything that you put into A came from X, and it was connected by a red edge previously. Similarly, you're putting things in blue and building up a blue clique there, and every time you do this, you're basically throwing away half the elements of the big set X. I'm not going to go through any calculation, but you can roughly see where a 4 to the k then is. That is, if X has at least 4 to the k vertices to begin with, then this will terminate with either k vertices in A or in B, and you have found a clique, a monochromatic clique, as they call it, a clique of one color. So your idea might be, if I want to reduce the base of this exponent, maybe I should have a cleverer algorithm than this, because in particular, x is chosen completely arbitrarily. So this paper came out. It came out in March 2023. It was accepted in June 2025. So the referees finally got back and everything was, okay by then. But Bhavik Mehta had formalized it in lean in November of 2023, so rather earlier than the referees. And then I thought I would have my attempt. And mine was done like a year before the paper was finally accepted. So this is the kind of thing people have been wanting, right? The proof assistants to get in there and check papers even before humans can, and where we can be pretty confident that there are no, well, there were, in fact, a lot of errors in the original paper. However, the final result should be pretty clear. So all that is that's simply the statement of setting up Ramsey things and saying the upper bound is for a certain positive epsilon bounded by for minus epsilon to the k for sufficiently large k, which is one of the many things that made this painful. So I need to say the mathematics here is not as sophisticated as some, but there are lots of numerical estimates. There's some kind of undergraduate level analysis. There's a certain amount of Ramsey theory. There's a lot of calculations, numerical calculations. And there's a lot of asymptotic reasoning, limiting arguments, and so on. Now, I just want to show you a little bit of the things we'll be playing with. This is by no means a full presentation of what's going on here. So they're talking about integers L and K. So in general, remember K is the size of a clique we're looking for, but in general, you could have cliques of two different sizes. So L then would be the size of a red clique if you're looking for a red clique having a different size from K being the color of a blue clique. There are the sets of vertices x, y, a, b. And as for the coloring relationship, now it looks like this. So for example, I mean, the red, remember, means, for example, all the edges between a and y are red, and so on. So they have a more complicated thing with these two sets, x and y. And I'm sorry, I never really figured out what y is doing there. Somehow it works. If you ask me who doesn't know the mathematics, yeah, I don't know the mathematics. I just went through the paper line by line. So there you had a slightly more complicated thing, which they call the book algorithm. Let me go back a moment. They call them books, apparently, because these wedge-like colored things are a bit like a book that has opened like this, you see. Anyway. So there is some standard graph theory, as it turns out. Luckily, we had done something with Chemeretti's regularity lemma earlier, and I had a little familiarity with things like edge density of a graph and so on. We don't need to look at these definitions very closely. I'm just giving you an idea what they look like. And this algorithm is, as it says, trying to build a clique in A, but obviously if it can't do that, then it will build a blue clique in B instead. But it's somewhat asymmetric compared with the original thing that we saw. Again, I don't want to go in detail through this, but simply to say there is a kind of computer program which has four kinds of steps described as here. They are just fancier version of the things I showed you for the simpler automaton, a thing they call degree regularization, the big blue step, and these red and density boost steps. They all move vertices around in different ways according to certain conditions. I guess I'd show you the big blue step because this is actually executable, but only in theory, or like maybe if you're God, you can execute this. Because, for example, it says, if there exists a Ramsey number, this many, that is Rk of L to the 2/3 vertices with such a property. So we do not, all the computer power in the world cannot even compute R of 6, 6. And this K and L will be very big numbers. So there is no, we cannot execute this, but it is executable in a technical sense. And in fact, the whole paper can be seen as a kind of exercise in program verification. Okay, now I just want to show you something of what I was contending with here. First of all, putting in the automaton is straightforward. This is, again, only a little chunk of it. A next state relation with, there are transitions for the 4 transitions I told you about. You know, this kind of thing is fairly routine. Primitive recursion, you know, sort of thing you could do in the 1980s. But as for a proof, right, this is lemma 4.1. This is the first serious lemma. And let me skip ahead and show you the full text of the lemma. So that's the lemma statement. That's the first, 7 lines of the proof. And skip that for a moment. That is the rest of the proof. What's that? Another 10 lines or something? No big deal, right? So why did it take me 4 weeks? Well, I will show you why it took me 4 weeks. By the way, the thing you have at the bottom there is the formal version of the same lemma. And the first really painful thing that I finally discovered was that all the claims in the paper are for sufficiently large L and K. This wasn't at all clear to me in the beginning. So every theorem, you see where it says big, this assumption big. This is like explicitly saying if L is big enough, subject to this parameter mu, then the conclusion holds. So they kind of left this ambiguous or implicit throughout the paper, which really threw me for a while. And then because every theorem has these bigness assumptions, you have to add them all up together, and they get more and more and more and more and more. And God knows, I've never tried expanding it out to see the full set of constraints on L here, but they are very big numbers. So let's look at part of this proof. It looks like fairly straightforward stuff. The first, and that inequality in the middle, the first thing holds by definition. Then you've got just 2 inequalities. That can't be very hard, can it? By the way, I did have to cheat from time to time because when I got stuck, I said, what the hell did Bavick do here? So I saw Bavick, I can't read lean very well, but I can read assertions. I said, wait a minute, why does Bavick have 2 over k? Well, it turns out it's because k can be as big as you want, and if you make k big enough, it doesn't make any difference. I find it kind of hard to think in this way, but this is how you have to do these proofs. This first inequality, there's some massive thing involving the summation, which is in the definition of the edge density. And so that's why this is only a part of the proof of that inequality here. Again, I'm just trying to show you what the material looks like. At least it is a nicely structured proof and all of that, but it is still, I would like to stand here and say that it's a legible proof, but you'd all laugh at me. Okay, second half of the proof. Now, whenever you start seeing let S be a randomly chosen subset, then you say, oh shit, but in fact, probabilistic proofs aren't that difficult, and you need another probabilistic proof to get some results about Ramsey numbers, which you need to even get started on this. So the 4 weeks, in fact, included a little time spent proving results about Ramsey numbers themselves using a probabilistic argument. So we actually know how you do this. You set up a probability space and all of that. So these calculations were, well, here's part of them. So at the top line, you see you're setting up omega, which is going to be the probability space. The This is a uniform distribution. That means the probability of each possible event is the same. So you go through this, you set up the boilerplate for getting your probability space. You see there's a word interpret, so we're using a locale here. And the general idea of a probabilistic proof is if you have a set and you prove using your probability space that the probability of something belonging to the set is non-zero, then bingo, you've showed the set is non-empty, and all you constructivists can go away and cry. But for the rest of us, we have exhibited, we know that the set is non-empty, which is all we care about. And this is how many things are done in this world. Okay, so that was crushing, and that was only section 4, and it goes on to like section 11 or something. So let me just give you a little grasp of what they are trying to do in the later sections of the paper. So remember, they have two sets, X and Y, and every time they do a step, they are throwing away huge numbers of vertices, maybe half of the elements of X or half of the elements of Y or whatever. So you need to know that the red density, that is the density of red edges, remains high, that the cardinalities of the sets remain high enough. And once you've got all these basic, if you like, safety properties, then they start extracting information. It starts to get weird here because now they're saying to prove a certain fact, they basically say, okay, set up the automata, you shove it in this stuff as initial values, you imagine running it, and then from the run, somehow, in a way I never quite figured out, you get your claims to come out of here. And finally, they build up in stages till they get their main result when they finally are able to set k equal to L and get their epsilon, which is very, as I said, something on the order of 0.001 to get the main result. Now, I wanted to switch topics slightly. What is really interesting is how much computer algebra is used in this proof. And I first want to mention how you do computer algebra in Isabelle. We can do all these things. So how do we do differentiation? We do differentiate, as everyone probably knows, you can do differentiation by a very simple functional program. That you just take the normal differentiation rules that you all learned when you were like 15 or 16, and you apply them one at a time. Now, what I've done here is I have deliberately crippled the approach so that instead of finding the derivative, it gives you like an intermediate stage. And if you see this thing e to the minus t, whatever, that I'm trying to differentiate, if you just apply the differentiation rules and do nothing else, it gives you this whole bunch of equations left to be solved. Oh, and this final p term, which I put in just so that we can see the derivative that's finally calculated. So there's a lot of equations, and then there's some further derivatives to be found. And if one were to keep doing this, the derivative would pop out, as you can see here. So if I just insert the command force, that will now force the simplification of those things, it will calculate the derivative. It comes out like this, which is not very legible, but I have converted it back into mathematics for you. So, and you can basically differentiate anything like this. If you need an integral, by the way, you just use maple or something, then take the derivative, check that they agree, and then by the fundamental theorem of calculus, you can actually assert that the integral of the one is the other. So you don't have to trust Maple's result. You can check it by proof. I have to be quick, but Emmanuel, are you here? Oh, he seems to have left. Emmanuel Iberl's real asymp package is wonderful. It can do all these things. And in particular, I need to know that things show that things hold in the limit, because this is kind of reasoning is used constantly in the paper. So, for example, if I'm interested in the limit of that thing, real asymp can calculate it, it can verify it, and it can even calculate it from nothing, in fact. Or this thing here, so that's a little o notation. If I want to know that the function n to the k is little o of c to the n, so it's a Landau symbol, just provide it to real asim, and bingo, they come out in both cases more or less instantaneously. Also, if you have exact calculations to do, there is something that will do that for us, this approximation thing. It can even do, so this last thing at the bottom, see, we have x ranging over a closed interval and proving some inequality involving x. That can get a bit slow, but that also is fully automatic. So what does it all have to do with the Ramsey proof? Well, as I said, all of those theorems, several dozen of them, I guess, are for sufficiently large L where the conditions on L, every time you find another inequality in the paper that in fact isn't true, you say, but it is true if L is big enough. So then you grab that little fact, add it to your bigness assumption, and it keeps getting bigger and bigger. And so you end up all these things like, L is greater than whatever, and that thing there, you see L isn't even, the L is in there. It's not even, you don't even have to even solve for L. You just have to put it in somewhere, and as long as real asim can prove it, you're sorted. So I would accumulate these things. First, I would check if they were even true, because I have no idea, but luckily I have a copy of Maple, and then prove them using real asim. And I told you we have these bigness things. Here's a different bigness one, a bigness predicate. You see it is referring to several bigness predicates from all the lemmas used in this theorem, plus further inequalities needed by the theorem itself. And then because I then worry, can I really actually achieve? Is there really such a big enough number? In other words, is this consistent? So I then have to go and prove that such a big enough number does exist. And it needs some calculations here, and finally a call to real asim to do the really hard work. Even, I'm afraid, can you see that 2 to the OK? This really freaked me out when I saw that. Luckily, I met a mathematics undergraduate who helped me. All that means is there is a function, which is a little o of k function, that can be inserted in there to make that property hold. And when I looked at this, I decided it was best to make these little o of k functions explicit so that I knew what I was dealing with. So you see that one there at the top of the slide is a specific function, which is o of k, and you can show that it's little o of k using real asim, and then you can use this for the claim up there that this particular monster up there is 2 to the o of k. So you see I simply have literally 2 raised to this particular o of k function. So I aged a lot in those 7 months or whatever. Wait, something went wrong here. Okay. Here's another line from the paper. I mean, you define all these things, and then you've got to prove it's greater than 2/3? Like, what the fuck? And in fact, what you do, you can call the approximation function. We have to show that a certain function is concave, so I have to take a derivative and do a certain other things. But if it's concave, that means that to show the inequality over the interval, I only need to check the endpoints, and I check the endpoints using the approximation method. So I'm just trying to say there's also a lot of computer algebra in this proof. And finally, one of the key results near the end, and I think, by the way, 2 to the minus 11 is our epsilon, the epsilon in this great theorem. So I had to show this particular inequality up there, which when you expand it out, turns into that. And the proof is by approximation. So it's a single call. And by the way, I think that uses something like 10% of the runtime of the entire development is in that approximation call. So what can I say? The actual formalization task was straightforward the whole time. My problem constantly was like, what the hell are they doing? Because I do have a mathematics degree, but I got it in 1977, and I never studied any of this. I didn't even know what a convex function was. Um, the computer algebra stuff was really useful. And there is a certain amount of legibility here. People have asked, like, what are the connections with Bavik's proof? So I asked Bavik, how did you do that? And you didn't have, like, this approximation and so on, and you didn't have real asim. And he just said, well, that's hundreds of lines. One of the things, I think the one I showed you, I think he said it was 200 or 300 lines. I can't remember. It looks incredibly painful. And yet his proof is only a little bit longer than mine. So he's got a very concise style. So that's the proof of the main theorem. And you see, it takes, what, 218 seconds is not so long to run. As I said, a good chunk of that is in 2 calls to the approximation method. And it took me, I guess, 2/3 of a year to get this far. Okay, that's it. I ran slightly over, I guess. Thank you.